All right, we're going to take a look at volumes of known cross sections. Now, I'll put out a companion video to this because visually this is kind of hard to see. So if you haven't watched that yet, it's only a couple minutes long. You might want to go watch that video so you can visually see what I'm talking about. Now, before we saw that volumes of known cross sections are solids who, if you take a cross section in a particular direction, you always get the same shape, but a different size. Unlike what we talked about the other day, a regular solid, not only when you cut it in a specific direction, you get the same shape, you get the exact same size as well. So for like a regular tube cylinder here, if you always cut it perpendicular, you always would get circles of the exact same size. However, if you have something like a cone, if you cut it kind of perpendicular the way I draw it here, you would still get circles, but those circles would be of different sizes. So if you do have a volume that has cross-sectional shapes that are all the same, how can you figure out the volume? So let's actually just take a look at one of these. Again, visually you might want to look at the video first. So find the volume of the solid whose base is defined by the region bounded by, let's make it easy. Let's go y is equal to x, y is equal to x to the fourth. Where slices are taken perpendicular to the x-axis. Okay, so let's start with this. First off, just like before when we were doing the volumes revolution, sketching the region is important. So we need to sketch the region bounded by these two curves. So since we want to find the region bounded by those two curves, we do need to find out where they intersect at. So let's see, we can factor out an x, we get x cubed minus 1. Good news and bad news, this is a difference of cubes, that'll factor, x squared plus x plus 1. And here we would set each one equal to 0. We get, of course, x equals 0, x equals 1. And to do this one, you would actually have to do the quadratic formula. I'm going to help us out. None of those solutions are real. You have two imaginary solutions for that. So these things only intersect at 2 points, kind of. So let's take a look at the first picture of the base. Well, x to the fourth kind of looks like a parabola with kind of a flat bottom here, so it kind of comes over like that. And y equals x, of course, is just that line. So you can kind of see the bounded region is this over here. So let me go ahead and get the rest of this out of the way. We really don't need those. And we know they intersect at x equals 0, so that's right here, and over here at x equals 1. If you want the y value here, that's there. All right, so we're saying that our cross sections are taken perpendicular to the x-axis. So the idea is when I take a slice out of here, I'm going to pull one shape out of there. Now, I haven't told you what the cross-sectional shapes are yet because we're going to do a couple different ones. So let's start out with the first one, a cross section of a square. So that means when I take a chop out of here, this little slice, the size of the shape I'm going to get is a square, which is going to have, of course, the same height as that width. So what I'm going to do is I'm going to come over here and always sketch your cross-sectional area. So I get a square. Now this square is going to have a slice, right? Because we took a little slice out of this. Now just like our volume, since we're perpendicular to the x-axis, that's going to be a little piece of dx. So that side right there is dx. So my question for you is, what is the volume of this one infinitely small slice? Well, the volume of a box is length times width times height. Well, we already have a width, or whatever you want to call it, a height or width, but I need to know what these two sides are right here, or basically what's the area of that cross section. Well, since it's a square, it's just going to be the side squared. So what's the length of a side? Well, that would be this length right here. Well, we know that that length would be what? The top curve minus the bottom curve. So this side here, which would be that side right there, would be, remember the top is y is equal to x and the bottom is y is equal to x to the fourth. So it would be the top curve minus the bottom curve. So this side here is x minus x to the fourth. So what would the little piece of volume be? I'm going to call this dV, right? A tiny piece of the entire volume would be equal to length times width times height. Length, now since this is a square, that's x minus x to the fourth, x minus x to the fourth dx, or I'm going to go ahead and swing it right here because we're basically done. That would be x minus x to the fourth squared dx. Now, since this is just one infinitely small slice, we need to add up all the slices, and where do we need to add them up? In the x direction. To add up an infinite number of things, all we got to do is integrate. So if we integrate this from 0 to 1, because that's what x runs from, x minus x to the fourth squared dx, that will give us our volume. So there's the volume of the entire shape if it had a cross-section of squares based off of the base being the distance between the two curves. Okay, so that's it. Not too bad. So what do? You draw your picture just like we did when we did volumes of rotation. Draw the side picture of what the cross-sectional area looks like. Find the area of this little piece and then just integrate in the direction that your representative rectangle goes. So let's try the same thing to, let's do cross-section of semicircles. Circles are tough. Well, unfortunately, or fortunately, not much changes here except for the picture. Unfortunately, I suck at drawing, so you're going to see what happens here. All of this is basically going to be the same amount of work. But what does it look like? Well, the base is still the same. We're going to end up with this kind of taco-looking thing when I draw it. Okay? The base is still this exact same strip. Notice I didn't change this picture at all. But now I need to find the volume of this shape. Well, what is that? Well, it's the area of the surface times dx, just like any of our regular solids. So what's the area of a semicircle? So the area of a half a circle would be 1/2 pi r squared. Right, the area of a circle is pi r squared, half of that. So the volume of this, a very small piece of that whole thing, dV would be 1/2 pi r squared dx. So now all we got to do is figure out what the radius is. Now, this is a little tricky. We just saw a second ago, since I know you all know what half of a circle is, I'm getting rid of that. We just saw that all the way across there was x minus x to the fourth. Well, technically that would be the diameter of that circle, so the radius would be 1/2 of that. Okay, so again, we're basically done now. A small piece of the volume would be 1/2 pi times the radius, which is 1/2 x minus x to the fourth squared dx. All right, so I'm going to do a lot here. I'm going to get all the constants out front of this integral because we're just going to integrate. That would be 1/4 and a half would be 1/8 pi times the integral from 0 to 1 x minus x to the fourth squared dx. Okay, so there we go. I just kind of cleaned it up and we integrated again in the x direction. Notice it's basically the same formula except for we have a constant multiple out front. Kind of be to expected because both shapes are defined by the exact same region, so they should have the same basic form, just one's going to be a constant multiple of the other. All right, so to find the volumes of known cross sections, sketch the region, draw your representative rectangle, go over to the side, draw a quick picture of what the cross-sectional should look like, find a little piece of dV, and then just integrate that across the region, and that will find you the volume.